I hope the modeling concepts were clear to all of you. If not, please go through it again because that will be needed in modeling techniques also. So what I'll do is that I'll expand on the modeling concepts, and now I'll go ahead and discuss the various modeling techniques. The first one is basically ER diagram. It is also known as entity relationship diagram, and it is used for OLTP relational databases or OLTP RDBMS. Now, it is used to define the relationship between entities. If you have seen in the previous topic, I told you the relationship between various entities vis-a-vis data, meaning that how the entities are related as far as data is concerned. We have one-to-one, meaning that for each record in one table, there is only one record in the other table and vice versa. Then there is one-to-many, wherein for each record in one table, there can be many records in the other table, but not the other way around. Then we have many to one. So for many records in one table, there would be only one record in the other table. Then also we have many to many, wherein for multiple records in one table, there would be multiple records in the other table also, and vice versa. So those are the relationships that I had discussed, and ER diagram shows those relationships between entities collectively for the entire system. It is a combination of normalization and data relationship, and normalization is something that is definitely needed. So if you have multiple entities, you will have to make sure that those entities are in 3 normal form at least. So all the tables should be in 3 normal form, and then we can go ahead and create the ER diagram. And these are the entities that we have talked about. We have customers, orders, sellers, order items, and products. Now these are the entities based on the data set that I have provided for the hands-on. Now let's look at the relationship between orders and customers. And what we'll do is that we'll go inside of the orders entity and we'll see for each record how many customers can be there. And then we'll switch gears and we'll get into the customers entity and we'll do the same thing for orders also. Okay, so we know that if we get inside the orders and we are defining the relationship between orders and customers from the perspective of orders entity. So now if I get inside the order entity, we know that for each order there can be only one customer. We cannot have more than one customer for a single order. And always do the relationship mapping using a single record. That would be useful. Now if I go inside customers, for a single customer there can be multiple orders. So it's a one-to-many relationship or many-to-one relationship between orders and customers, and one-to-many relationship between customers and orders. Why? Because as I said, you have to look into a single record only. So now you know that between customers and orders, this is how the relationship would be. So for a single order in the orders table, there can be only one customer. That's why we have this standing line. And for a single customer, there can be multiple orders and there can be 0 orders also. So that's why we have these multiple lines. So now let's look at orders and order items. Let's look at one order and get inside the orders entity. We know that for a single order, we can have multiple products or multiple items. So for each record in orders, there can be multiple records and order items. So we know how the relationship would be between orders and order items. Now let's get inside order items entity. For every item, there can be only one order. Of course, the same item cannot be there in multiple orders. So it is also a one-to-many relationship between orders and order items, and many-to-one relationship between order items and orders. Now, what about order items and products? Now let's say for one order item, there would be only one product. There cannot be multiple products in a single item because the item itself is single. Now, what about products? For each record of product, there can be multiple order items because products describe all the products that are there in the shop. So the same product can be there in multiple items also. So now if we see the relationship, it is like this. Each item, for each item, there would be only one product, but for each product, there can be multiple order items. This is how the relationship would be. Now let's see the final one between orders and sellers. For each order, there can be only one seller, but for each seller, there can be multiple orders. So that's how it is. Actually, this should have been with order items, but in the data that I have generated, I have not put any seller ID in the order items. So that's why the relationship is like this. But typically, there would be relationship between sellers and order items. So for each order item, there can be only one seller, but a single seller, for each seller record, there can be multiple order items. So the relationship would be like this: one to many between sellers and order items, and many to one between order items and sellers. So this is what ER diagram is. And it is used to represent the relationship between entities in OLTP databases also only. I mean OLTP relational databases. Then you have another modeling technique that is called dimensional modeling. And dimensional modeling is used for OLAP relational databases or data warehousing systems. Dimensional modeling is used in data warehouses and it can also be used in data lakehouse. So if you have a lakehouse, we can use dimensional modeling to define the data model in the lakehouse also. And one important thing about dimensional modeling is that it revolves around something called facts and dimensions. Facts and dimensions are nothing but tables. These are entities, but these are named differently. One set of tables is called facts and the other set of tables is called dimensions. I'll tell you what are the differences between the two. And the relationships are defined between fact and dimension tables only. There's not too much of relationship between dimension and dimension tables, and that's how dimensional modeling is. So let's get into dimensional modeling, and it might be a little concept heavy, so please bear with me. The first one is facts. So what is a fact? Now the English word fact means data points. Basically the quantification that something has happened. There's no abstraction to it. If we say that it is for a fact, we know that it has happened. And we can prove also that it has happened because there are data points. There are physical presence that something has happened, and that's why we call them as facts. Similarly, in the data warehousing system also, we have fact tables. So fact tables tell you that something has happened in your business. And it contains the numerical performance measurement of the business. So this is the quantification of your business, meaning that this is the fact of your business. This is the data point that runs your business. And when we talk about data point, we essentially are talking about numerical data points because numerical data points are the only things that can be used to quantify a thing or quantify certain things. So same is the case with business process also. If we have numerical measurement, we know that there's a quantification of the business. And these are the facts of a business, as I have told you. These are the physical things that happens in your business, or these are the things that define your business. Now, one very important thing about fact tables is that it should contain only numerical data. It cannot contain any non-numerical data, meaning that there cannot be any data which is not quantifiable. So those type of data should not be kept in fact tables. And when you talk about numerical data, there are three types of numerical data. One is additive. It is also known as additive fact tables. When we say numerical data or a fact table is additive, it means that we can apply numerical functions on the attributes which has numerical data across all the dimensions, which we'll talk about. Then semi-additive means that numerical functions can be applied across only a few dimensions, not across all of them. And then we have non-additive, which tells you that numerical functions cannot be applied at all, even though the data that we are storing are numerical in nature. So these are the three different types of fact tables, or the data that fact tables contain. All are numeric, but some can be additive, meaning that we can apply numerical functions like average, sum, maximum, minimum, etc. across all the keys that we define. Some are semi-additive, meaning that we cannot apply the numerical functions across all the keys. And some are non-additive, meaning that we cannot apply the numerical function at all. Numerical data is that data that are used in the calculations. Now this is the table, this toned down version of the table that we had seen in the first normal form. And we have order ID, order date, delivery date, item ID, description, price, order items, customer ID, name, date of birth, email, and address. Now, if we have to create a fact table out of it, we have to remove all the non-numerical data. So here, if you look at the columns, order ID, even though non-numerical, we need it to identify an order uniquely. Order date is definitely not numerical. Same is the case with delivery date, item ID, description. So these are all non-numeric data. Order price is numeric data because we can apply numeric functions like sum, average, minimum, maximum, etc. on this column, on the order price column. Same is the case with order items also. We can add the order items, we can find out the maximum also, etc. Customer ID is not numeric at all because this is an identifier which uniquely identifies the customer. Same is the case with name, date of birth, email, and address. So if I have to carve out a fact table from this first normal form, I'll have to remove all the numerical columns, which are these and these. If we create a fact table from this entire first normal table, we'll only have order ID, order price, and order items. Order ID is needed because we need an unique identifier to which the order price and the order item belong to. Otherwise, if you do not keep order ID, order price and order items will not make any sense by itself. So that's why you need a identifier for these rows also. So this is how the fact tables would be. Of course, you'll have to combine the columns, which would contain only the numerical data and unique identifier. Then we have dimension tables, which are different. Dimension table contains description of the business entities, or typically the non-numeric data. For example, again, we have the same table wherein we have order ID, order date, delivery date, etc. Now, if you see, we have non-numeric or business representation. So order date, delivery date, item ID, description, customer ID, etc. These are information about the business entities, but they are not numeric data at all. So there has to be a way that the fact table that I had just shown you in the previous slide should have a pointer to these records also. And these records or these columns or these attributes would go to dimension tables. So I'll have to modify the fact table in this way. I'll have to add the item ID, customer ID, date key. Now, item ID is basically the item ID which would point to the item table. Customer ID would point to the customer table, which would contain the description of customer. Date key would basically would point to the date table, which would describe the date. And all the other entities related to item, customer, and date would be put in dimension tables. So the first dimension table would be like this, which would contain the item ID and description. So if you see, there's a pointer between the fact table and the dimension table using the item ID, which is the foreign key relationship that we had discussed. Now this is a dimension table, if you see, because we have the item ID and its description. There's no numerical value to it, but it is a description or textual description of the business entity. Similarly, would have customer table, which is also a dimension table, and it would contain the description of the customer. which is also a business entity. So all the customer related information have been put in this particular table, and there's a pointer between the fact table and the dimension table using customer ID. And then we have date table also, wherein we can put date key, year, month, day, and other tables and other columns. I'll talk about date dimension later on. And so these three, the item table, the customer table, and the date table, these are called dimension tables because they contain the description of the business entities. And it does not contain any quantifiable numbers or quantifiable attributes. So if you see, even though you have item ID and description, we do not have the item price here because we have put the item price or the quantifiable attribute in the fact table. Now, this particular table has been broken down into one fact table and three dimension tables. And this is called dimensional modeling. There's one more feature of dimension table, that dimension tables do not change as much. Right? So if you think about it, you will not add item pretty frequently unless there's a new release of the product. So let's say you have item ID 100 as iPhone, maybe iPhone 15, and item ID 101 as iPhone 16, which would happen only once a year as of this recording. Similarly, item ID 102 may be for iPhone 17, which would happen after a year. And same is the case with customer also. It's not that a lot of customers are added on a regular basis. The customer dimension, if you think about it, is not that dynamic. So the frequency at which customers are added is less relative to the frequency at which order is added, and order drives your business. This is the process that drives your business. So this is a business process. Same is the case with date table or date dimension, and I'll talk about date dimension later on. So these are the three dimension tables, and this is the fact table. So I have broken this entire table into 4 tables now. Now if you go further, this schema that I have defined using dimensional modeling is called star schema. Why? Because we'll have the fact and dimension tables together in the form of a star. So this is the order table or order fact. This is typical naming convention that the fact tables are named with the name of the table followed by underscore fact. Then these are the attributes or the columns of the fact table: order ID, item ID, customer ID, date key. All these combined together would form the primary key. Then we have the quantifiable attributes: order price and order items. Then we have multiple dimension tables like customer dimension. And again, this is the typical naming convention that the dimension tables should be named as the name of the table followed by underscore dim. Then these are the attributes of the dimension tables. And this dimension table has customer ID as the primary key. Same is the case with item dimension. So item underscore dim, item ID being the primary key, and item description is another attribute. And then date dimension or date dim, where date key is the primary key, and then we have year, month, day. And we have relation with all these tables. So all the dimension tables are related to the fact table. So if you look at it, this forms like a star, one center and multiple arms. So that's why it is called star schema. And that's where the name comes from. So this is what a star schema is. So we create a star schema by following the dimensional modeling patterns. Then we have Snowflake schema, which is an extension of star schema. So Snowflake schema is basically star schema plus 3 normal form of dimension table. I have these fact tables and dimension tables. I have order fact table and 3 dimension tables. And in customer dimension, I have address and country ID, which can be normalized further. And I can create a third normal form with another table with country dimension. And the country dimension is related to customer dimension. So it does not have any relation with the fact table. It is related to the dimension table. So this is a third normal form, or these two tables are third normal forms. And These are dimension tables. So this is called a Snowflake schema, where we use the star schema plus the third normal form of dimension tables. One of the very important components of data warehouse or dimensional modeling is defining grains. So what is a grain? First of all, grains pertain to fact tables only. We do not define grains at dimension tables. So define grain at fact table, and it basically defines the level of granularity at which the records are stored in fact tables. This is the definition of grain. Also, there's another definition, like if you have to simplify it, it is a combination of columns at which records in a fact table are unique. Then if I have to extend or simplify the definition further, it is the level of detail that the data represents in fact table, or again the granularity of fact table. It also are the rows that depict the main functionality of the business, product, and application, basically the business process. Grain can also be thought of as the primary key of the fact table. So when you define grain, you'll have to know what should be the primary key of the fact table. So whatever is the primary key of the fact table, combination of all those becomes the grain. So let's say I have this order fact table and I have order ID, item ID, customer ID, date, order price, and order items. So what is the grain here? The grain is basically the individual order items, because the primary key is order ID and item ID. Even if we remove, let's say, customer ID and date, the combination of order ID and item ID would always be unique, because this is how you run your business, or this is the business process. Whenever someone buys something, they buy the lowest granularity at which someone can buy something. In case of retail, is the item. So individual item drives the business, drives the retail business. So that's why this fact table, the grain of the fact table is individual items. And if we combine item order ID and item ID, then we get the unique key also. So now if I have to tie it back to the definition, so it is the level of granularity at which records are stored in fact tables. And records are stored at individual item level. If you see here, the order ID and item ID are the primary key. Now, because we have customer ID and date key also, we can include customer ID and date key also in the primary key. But if you remove customer ID and date key, and if you do not want any information about customer and date, only order ID and item ID would be enough to define the uniqueness of this fact table. So that is the grain, which is the level of granularity. And it is the combination of columns at which records in a fact table are unique. As I said, if I add all four of them, obviously they would be unique. But if you think about it, it is basically the order ID and item ID which are actually unique. We have put customer ID and date key because we want to find out the customer details and the order date and delivery date, etc. Other definition, level of detail that the data represents in fact tables. So what is the level of detail? The level of detail is individual item, which you have put here. Also, individual item or rows belonging to these items depict the main functionality of the business or the product or the application that we are running, because we are talking about a retail use case. And as I already told you, that the lowest level or the lowest granularity at which the business is run is individual item. You cannot go beyond that. I mean, you cannot break the item further. We cannot sell half an item. It's always unit of item. So that's why that is also called a business process. So the rows that I am defining here depicts the main functionality of the business, and it also is the primary key of the fact table.